guanosine triphosphate, it can be CTP, it can be which one is going to be TTP, another one. So these are the 4 trinucleosides are available in the cell. So they will take whichever can bind to this base, that will come, and then the DNA polymerase will do a catalyzer reaction. So what will happen? This is the triphosphate. This red bond, it will be broken. So it will release the diphosphate, leave the molecule, and then the hydroxy group from the growing strand. So this hydroxy group is coming from the growing strand, that will make a new bond with the phosphate. So a new base now would be attached to the growing new strand. And that's the way continuously the nucleotide is going to be growing. Now let's go back to this figure again. So now this polymerase has some kind of limitation. That limitation we need to know. What is that limitation? It can only synthesize if we look at the new poly strand, that can be synthesized from 5' to 3' end. Because the NTP that is coming, the incoming nucleotide, that gives the phosphate group, and the growing polynucleotide that gives the 3' hydroxy group. So now the polynucleotide, the new one, that is going from 5' to 3' end, and the polymerase then needs to climb the old template from 3' to 5'. So it can move only from 3' to 5' direction along the old template strand, and the new one would grow from the 5' to 3'. So this can grow, this 3' to 5' one, that can grow continuously, and we call it the lagging strand. This strand is called lagging strand. Sorry, the leading strand, not the lagging. Leading strand, it can grow continuously. On the other side, this template strand, because the polymerase can move only 3' to 5' direction. So this old template, this 3' to 5' is going to opposite direction. This is our replication fork. So replication fork is opening continuously, and this one is moving to the replication fork direction. So the leading strand is forming towards that direction. But this one, because polymerase is moving that way, it cannot be synthesized continuously. Rather, they synthesize small fragments. Those small fragments we call as the Okazaki fragments. So later, another enzyme that is called the DNA ligase, that actually connect the number of Okazaki fragments to give us the another polynucleotide strand. And this strand that is not growing continuously, we call is the lagging strand. This one is the leading strand, this one is the lagging strand. So lagging strand is growing in the opposite direction, and the leading strand is growing to the replication fork direction. So there is many information actually that you need to understand. So you need to actually read the information to understand it better. Now let's see the video on this, that what I was trying to say. That may help you little bit better.
This means that wherever there's a T in one strand, there will be an A in the opposite strand. And wherever there's a C, there will be a G in the other strand. Each strand has a 5' end and a 3' end. The two strands run in opposite directions. This determines how each strand of DNA is replicated. The first step in DNA replication is to separate the two strands. This unzipping is done by an enzyme called helicase and results in the formation of a replication fork. The separated strands each provide a template for creating a new strand of DNA. An enzyme called primase starts the process. This enzyme makes a small piece of RNA called a primer. This marks the starting point for the construction of the new strand of DNA. An enzyme called DNA polymerase binds to the primer and will make the new strand of DNA. DNA polymerase can only add DNA bases in one direction, from the 5' end to the 3' end. One of the new strands of DNA, the leading strand, is made continuously, the DNA polymerase adding bases one by one in the 5' to 3' direction. The other strand, the lagging strand, cannot be made in this continuous way because it runs in the opposite direction. The DNA polymerase can therefore only make this strand in a series of small chunks called Okazaki fragments. Each fragment is started with an RNA primer. DNA polymerase then adds a short row of DNA bases in the 5' to 3' direction. The next primer is then added further down the lagging strand. Another Okazaki fragment is then made, and the process is repeated again. Once the new DNA has been made, the enzyme exonuclease removes all the RNA primers from both strands of DNA. Another DNA polymerase enzyme then fills in the gaps that are left behind with DNA. Finally, the enzyme DNA ligase seals up the fragments of DNA in both strands to form a continuous double strand. DNA replication is described as semi-conservative because each DNA molecule is made up of one old, conserved strand of DNA and one new one.